Morning. My name is John Allen Pascoe. I'm assistant professor at the Delft University of Technology. And within the D-STANDART project, I'm the work package leader of the work package dedicated to materials characterization testing. And today I want to present to you our vision for how we will do fatigue evaluation of materials, of composite structures in fact, and also present some of the first results from the D-STANDART project. So D-STANDART is a European Horizon Europe project. So we have a large consortium, 9 partners. We are led by the Netherlands Aerospace Center, NLR. We have the universities of Twente, Bristol, and TU Delft as university partners. The National Composite Center as another research organization. And then Hexagon, ELAB, Suzlon, and ICOMAT as industry partners. And together we are trying to solve a problem. What problem? Well, the following. We're at JEC, so I don't have to explain to you all the advantages of composite materials. And what probably most of you already know is that the first generation of composite materials, analysis, failure analysis was not so easy. Getting really consistent material quality was not so easy. And so we compensated by increasing safety factors, by having knockdown factors, quite generous margins in our structure. But over the past decades, we've become better at analysis. We've become better at quality control. So now we would like to make better use of our materials to bring down those margins and use our structures more efficiently. But that means we now have to worry about a new issue, which is fatigue. Now, the metals community has a solution for that. They developed this testing pyramid approach. We start characterizing materials at the coupon level. Then we go up the structural complexity ladder until we get to a full-scale test. So great, right? Problem solved. Well, not so fast. Because the thing is, if you try to apply this idea to composite materials, what you're faced with in the current state of the art is that each laminate, each layup you think of, is a new material. And you have to redo this entire pyramid for each laminate. Right? Which means that composites, great, you can tailor them, you can have every layup you want to exactly match your force paths, as long as it's one of the 5 layups you've already tested, because otherwise it's really expensive to do all of this again. Right? Another issue is illustrated on this slide. Because testing and doing fatigue evaluation is so expensive, so time-consuming, typically only do that right near the end of your development, which means that your confidence in your product, your knowledge about your product, only appears when it's too late to do anything about any of the problems you might find, right? Because it's now really expensive to make any design changes. So what we'd like to do is to push that curve to the left and say, okay, already at a very early design stage, can we get knowledge about the fatigue behavior of our product when it's still cheap, relatively cheap, to make any design changes to improve that, right? Or to make conscious trade-offs there. So if I reformulate that scientifically, there is a need to have a better understanding of the mesoscale fatigue effect, so we can account for different layups, and to transfer that understanding to predict the behavior of large-scale structures, so we don't have to test every single laminate we might want to put in there. So that is what we are aiming to do in the D-STANDART project. We're aiming to develop rapid characterization methods to allow early stage durability modeling at an early design stage, and also include the operational environment. I will not talk too much about that today. And we're going to achieve this by enabling minimal and accelerated testing, so do the tests we do faster and do as few tests as possible, but ensuring, of course, the right coverage. And using artificial intelligence or machine learning to generalize those results and cover everything that we do not test. And with that, we aim to reduce time to market for composite structures, reduce material wastage, and potentially increase the lifespan of products, or, as you'll hear on Thursday in the talk by John Taylor, have a more conscious trade-off between lifespan and increased life cycle impacts. Just to give you a quick idea of where we are, this is the timeline of the project. We're in the last 9 months. We finished most of our characterization testing. We're quite far advanced in our model development. And in the last 9 months, we are going to validate our approach. So I'm going to show you some initial results from this part, and our vision for how we're going to develop the model and how we're going to validate all of that. Right. So let's start with the results so far. First of all, let's look at the accelerated testing, which we're achieving by high-frequency testing. So we have a rectangular coupon. Here you see the side view. And in that coupon, we've made a cut at one location. So we have a small damage initiation by cutting one of the plies. And then we excite this coupon with a vibration in the center at its resonance frequency. So somewhere in the order of 200 hertz. And what we then measure is the response of the coupon, and especially the phase lag between the excitation and the response. And that's what we then see is that that phase lag is extremely sensitive to damage initiation. Right? So as soon as there is any small onset of damage growth from that initial cut, we will pick that up in the phase response. And that means we can very rapidly characterize delamination onset or the fatigue strength of the material. And because the test is running at hundreds of hertz, one test you can do overnight, right? So in a matter of days or weeks, you can characterize really your fatigue onset curve, right? And do very rapid material screening, get very rapid input into your design. The next thing we've been looking at is the effect of fiber orientation to try and take these different layups into account. Our starting point is some standard tests. Those of you that do fracture mechanics tests of composites will recognize them, right? So we have the DCB test, the ELS test. But these tests in the standard use unidirectional layups, where we've taken a step further to go to multidirectional layups. So let's start with the mode 1 results. Well, this is rather a busy graph, so I'll walk you through it slowly. This is a Paris curve. So on the vertical axis, we have the crack growth rate. On the horizontal axis, we have the strain energy release rate. So basically, the driving force for crack growth, right? So the further we are to the right, the more load we are applying at the crack tip. The further up we are, the faster the crack is growing, the shorter our fatigue life. Now you see the different colors, they correspond to different interfaces that we're testing. So let's start with the blue circles. That's a 0-0 interface. What we see then also is there are different shades. They correspond to the initial crack length at the start of the fatigue test. And what we see, and what we would expect from literature, is that as you get a longer and longer initial crack, you develop more and more fiber bridging, which creates more resistance to the delamination growth, and so your curve shifts to the right. What we see here for the blue circles, it's a relatively modest shift. That's the 0-0 case. If we go to a 0.45 or a 0.90 layup, we see much larger shifts, right? So we see much larger effect of that initial crack length due to all kinds of toughening mechanisms that occur in these multi-directional laminates, right? So we mainly see effect at long crack lengths. At short crack lengths, it's all relatively close together. Right, it's already indicating, okay, if we have different layups, we have to test all of them. Not so great. And you might say, okay, but I'm willing to accept a more conservative approach. 0-0 looks like the worst case behavior. Can I get away with just testing a 0-0 layup? And you look at this, you say, yeah, okay, that should work, right? Gives me at least a conservative answer. Except, this is the mode 2 behavior. And what we now see is that the 0-0 layup is in fact the least conservative answer, right? The 0.90 interface is the one that grows the fastest for a given load. Right? So unfortunately, which interface is the most conservative depends on the loading mode that we are applying. Right? So we can't get away with just testing 0-0. Is all hope lost? Well, there are some other things we can do. Here's an example we presented last year at ECCM using artificial neural network, which was trained on the 0-0, 0.45, and 0.90 layup, right? And then made a prediction for a 0.15 layup. Right? You see in green the prediction, in black the experimental results, again a Paris curve. So pretty good match, right? And I want to emphasize again, this model did not see the 0.15 data, right? This is a blind prediction from the model. So gives us some hope. We don't have to test every single layup. If we tactically map out the design space, we can interpolate between using something like machine learning. But there are more features than just fiber orientation we may have to worry about. Yeah, there may be things like wrinkles, other manufacturing defects, or deliberate design choices like ply cuts, ply drops. Of course, one approach is to make a high-fidelity model, right? Here we see an example. So this is a coupon, probably about the size of this clicker, but larger, with a wrinkle in there. And if you model that in super high detail, right, you have all your plies modeled ply by ply, you have all the interfaces with cohesive elements, you give space also for matrix cracking. You can see that you can quite nicely model the real damage patterns that we get, right? We can also get a relatively accurate prediction of the stiffness drop of the specimen, so that's all great. But all of you who are really in industry say, okay, that's nice, but when I'm modeling an entire wind turbine blade, one of my elements is the size of one of those coupons, right? So how does that work? We have a bit of a paradox there. We need to model all of this complexity to get the fatigue behavior right, but there's no way we can afford to do that on a full-scale structure, computationally. And that is where we bring in machine learning. Right? So this is the vision we're developing within D-STANDART. We start with experimental data, tactically chosen to map out our design space. We use that to validate high-fidelity models at a mesoscale, so at the scale of centimeters by centimeters. When we are confident that our high-fidelity models can accurately tell us what's going to happen, we use that to generate synthetic data, right? To fill in the spaces in our gaps in our test matrix and test all these layups that we don't have time to test in the lab. With that synthetic database, we feed that into an AI model, which produces a surrogate model, right? So that surrogate model captures all this material complexity and tells us, okay, if you have a material with this layup under these loads, this is how it will degrade. But because that's captured in that surrogate model, it runs much faster and now becomes computationally possible to integrate that into your macro-scale, full-scale finite element analysis, right? So you have all the complexity, but in an affordable way. And then we also have a digital thread tying all of this together, which is a supporting infrastructure that allows one for the data transfer from one to the other, but also very importantly, it gives you traceability. So from your macro-scale finite element analysis, which maybe supports your certification, you can trace all the way back to which experiments did I do, which batch of material did those specimens come from, right? So you have full traceability and a real audit trail for your certification. So let's zoom in a little bit more onto what we're doing there with the machine learning, because I haven't talked too much about that yet. So in the machine learning, we are making use of Gaussian processes with adaptive sampling. And what that means, in a nutshell, is that when our AI surrogate model is trained, right, it gives us predictions, but not just the prediction, but also the confidence of that prediction, right? We get an uncertainty band around the behavior it's predicting. And if we decide that the confidence is too low, for example, because you're trying to predict in a region where we don't have enough data, well, then we can feed that back and specify a new finite element run, or in future you could even specify a new set of tests, right, to supplement your database, retrain the model until you're happy with the confidence you're getting, and then you're done. This approach also means you can do it step by step, right? You can start with a certain design, and then we say, I now have a new design, I have a new layup. Then you only supplement the database with what you need to support that new layup. Yeah. So does all of that work? Of course, we need to prove that. So we're working on two validation cases. We call them the aero demonstrator and the wind energy demonstrator. So the aero demonstrator is a specimen with a quite strong ply drop, somewhat representative of fan blade attachments, which is going to be loaded in combined tension and bending. And then we're also going to add in various hole sizes to see can we capture the fact that without the hole the damage would initiate in the ply drop, with the hole at some point it will move to the hole. And then for the wind demonstrator, we're looking at spar caps made from pull-throughed carbon fiber planks. And so here we have not a ply drop, but a plank drop, because we start with 3 planks going down to 1. And again, we're trying to see, can we model this fatigue behavior in this plank drop specimen correctly, using data from coupon testing and advanced modeling. So that went rather fast. So let me summarize. What we've seen is if you want to do a proper durability fatigue assessment of your composite structure, you need to characterize also the layup effects. You can't get away from that, right? You need to capture that complexity or you're not going to get the damage propagation correct. That is computationally very expensive if you do it with high fidelity modeling, but by using a surrogate model, we can capture that complexity and boil it down into something that can run within a macro-scale finite element analysis. And that gives us the possibility to do durability modeling and life cycle analysis at an early stage in our design, when it's still cheap, relatively speaking, to make any design changes because of that. To conclude, if you say, that all went a bit fast, I'm not so sure about the fatigue of composites, we have on our webpage, the D-STANDART Academy, we have an online set of training materials that you can use to learn more about fatigue in composites, even some hands-on exercises with some of our data from the lab that you can play around with. And if you would like to discuss further about how we do this fatigue analysis of composites, we're right over there at the booth, so please come talk to us during the rest of the day. Thank you very much. Yeah, we have, I think, time for a couple of questions, if there are any. Yeah.
Hello, I'm Filippo from Fincantieri in Italy. I would like to ask, sorry, it's maybe a very stupid question, but you showed us this pyramid of the how the fatigue analysis and validation is based on a very high level, scale up of the model. And so you showed us at the end that you validated your model with small tests, but are you planning to validate it with the pyramid?
So within the scope of an EU project with budget and time limitations, this is as far up the pyramid as we get. But we hope that it shows that, okay, we can take coupon level data, we can use this modeling approach to scale it up. And then of course there would have to be a follow-up to see, does it work when we go even further up the pyramid? But at least we hope that the concept is demonstrated.
Hello, Seçkin Marti from Turkish Aerospace. Thank you for my presentation. I would like to ask about the test frequency. You have said that 100 hertz, right, as far as I know. Have you ever considered the temperature effect of the material? Since, it takes, instead of weeks, you said one.
Yeah, of course. Yeah, so it's always a worry about the temperature increase. So the temperature is monitored during the test. What we've seen is that the temperature increase is relatively modest. So it's 10, 20 degrees, so not too bad. And additionally, we've also done this test at different temperatures so that we can then experimentally back out the temperature effect if there is a temperature increase.
Actually, based on my knowledge, when I exceed the 6 hertz or something like that for the coupon level samples, it goes like 70 degrees or something like that. So that's why I'd like to learn how it goes. Or are you cooling it or something like that? Or just a normal way?
No. No. So if you want the full details, I think later this afternoon or tomorrow we'll have the people that have done these tests. So drop by the booth. They can explain in real detail, but it's not actively cooled.
Okay, thank you.
So my question would be, did you have any contact to certification officials, how they think about the method? Are they willing to accept any like this, or is this a bit early?
So I think we're a little bit early for that. We have tried to find some contacts. I think the tricky thing is, especially for example in aviation, EASA, they like to certify a product. So if there's not a product attached, they're not so quick to really give you an opinion. But that would be a next step. I think first we need to validate for ourselves to show, okay, this works. But definitely, yeah, we need to be in contact with certification authorities and see what they think about it. I think in general there's some skepticism always towards modeling. I don't think we can get fully away from a full-scale test in the end. But I think even for design, if it helps you to optimize your design and helps you to have confidence in the outcome of your full-scale tests, even if the certification authorities don't directly accept the model, at least you've de-risked your full-scale test. All right, I think that was my time. So thank you very much for your attention and enjoy the rest of the JEC.